Nice to meet you. The dinner? Oh, I have a hard time remembering. What was your name? Jenna. I'll probably say. I appreciate that. One letter is easier than a bunch, but I'm not accustomed to being in.
What's your name?
Hi.
Thank you.
I need to write a bunch of matrices. Okay, so you're going all in that.
Yeah.
What's your project?
That's a fun. Yeah, it's not like a super fun, you know,
That's awesome. Yeah. Not
pretty much a lot of them. I was after better, just doing it, then.
yeah, he's
I do tell me what I can do, but I street.
he can be mean and pretty so that's true. He's a big body, he's just
So you choose to really look at
I'm in the conference here. Thesis. Thesis under Dr. Thomas. Yeah, is it the one, are you referring to the one I'm doing, or just in general? He's been doing later cavitation.
The one that I helped with back in the day, he was using that steady state research.
Yeah.
For a cooling system.
For cooling system. Yeah, no, I'm still, actually, then you say laser. Yeah, one thermal cavitation. But we're doing it on a micro channel. So it's 1.5 millimeters across. And then we're that creates. So like, how was it big again, or like? How big did it get? Like, I don't know, it's supposed to just like.
I remember it's been 4 years ago, we had to stop when the campus locked down.
Okay. That sucks. Yeah. I've never sent this first master's under his tutelage. So good.
I'm also had.
You know, you also put that, because I don't know, you really because anyone will be speaking, so I.
I was with vegetarian for 6 years. So I know the field.
For me, there was like
Yeah.
it was like
Pita bread and hummus. It's funny, yeah.
You know what's funny, like, one week or- Okay.
It was a- I mean, premium, so you can't really. I didn't eat the leftovers, I had, my name's Tom. Okay, nice to meet you. We're doing a project now, or is this now? That's project. Sure.
I'm going to have, Tina Robson make one of her rovers.
Oh, that's cool, yeah. She's good teacher. Or short type. It's mostly focusing on the features of the lift mechanism. He's doing some project with her right now.
So he's like.
Not sure. I mean,
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, hopefully everyone got my email today. So I apologize for a bit for the confusion. I know originally I had planned an ANSYS activity for today. But in this class, we're only going to be able to do two. And so and the second one is not going to happen until like week 7 or week 8. So I thought it'd be a little bit more useful to kind of cluster those two activities together. Just so that, we do, because I think what happened last time when I taught this class, I taught ANSYS at the beginning, and then we went over all this theory, and then we went over ANSYS again, and then everyone forgot the ANSYS, and then it was kind of a mess. And so I decided to kind of push the ANSYS kind of later on, and then we'll just kind of start building up the theory from now. And then once we do get to the ANSYS, that'll kind of be at a nice kind of breaking point in the semester. So it'll be kind of like a nice break between all the theories. So plus I was a little bit late in sending out instructions on how to install ANSYS. And so that's kind of the plan. So we're not going to do ANSYS until week 5. But if you didn't look at my email today, I did send out my previous activities as well as their video tutorials. And so if you were interested in learning ANSYS right now, so let's say if you have an application at work that you're interested in learning it for, you can check those out. So I think I gave the step-by-step instructions as well as kind of the video walkthrough of it. So definitely check those out if you were interested in ANSYS. Okay. But for today, what we're going to be doing is we're going to be introducing a method called the direct stiffness method, which is going to be our main topic for the first half of the course. Okay, so we'll introduce it today. We'll start building up the theory, and we'll kind of explain how this is related to the finite element method. Well, it is the finite element method, just a certain form of it. Okay. All right. Any questions I can answer before we get started for today? Okay. All right, so let's go and get started. So what we're going to cover today is the introduction to the direct stiffness. Oh, one thing you'll notice too is that I moved a lot of the MATLAB review to kind of later on, because we're not actually going to be doing anything with MATLAB until week 6, 7, 8. So I'm starting the theory a lot earlier this time. We're going to build that up, and then we're going to see how MATLAB can be used to implement these things. And so most of the software stuff will kind of push pushed to later to kind of make it more relevant. Because I think last time I taught this, I did all the MATLAB stuff in week 2, but then we didn't use it until week 7. So everyone forgot the MATLAB stuff and we kind of had to relearn it all. So yeah, rearranging things a little bit, but hopefully it'll be for the better for everyone. Okay, so let's talk about the direct stiffness method. Okay. So the direct stiffness method is one implementation of the finite element method. Okay. And so you're probably looking at that statement and kind of wondering what that means, right? So what do I mean implementation? Finite elements, there's actually lots of different ways to implement the finite element method, right? Finite element, all that really means is that you take a discretized model, so you take a mesh and you turn a complicated differential equation into an algebraic system. Okay. How you actually achieve that, there's lots of different ways to do that, and the direct stiffness method is just one way to do it. Okay? It's a really nice place to start when you're first learning finite elements from scratch, because on the one hand, it captures what I think are kind of the main, all the really main parts of the finite element method, and so it's good for kind of analyzing all the steps kind of in totality, but it does simplify some of the more math-heavy parts of the method. Okay. So it's a good learning tool. I wouldn't say that I wouldn't say that it's used in a lot of practical problems, but it's a really good place to get started. I'll put that in quotes, the mathy parts. Okay. And unfortunately, you won't really get an appreciation for that simplification until probably the second half of the class, once we start going over the Fullerton method. But trust me when I say that it simplifies a lot of stuff. Okay. And another thing that I like about that is that the way that it simplifies these mathy parts is that it does so from a very kind of intuitive, kind of physical perspective. And so it takes concepts that you've learned in other classes, mostly solid mechanics, and then it turns it into kind of an FEA method, which is nice. Okay. Okay. So that's the stiffness method, or at least kind of the reason why we're approaching it. So let's kind of get started too. So the first aspect of the stiffness method that we need to go over is the concept of a stiffness matrix. Okay. And so the idea with the stiffness matrix is actually quite simple. And to introduce it, I'm going to bring up something that you've probably seen in a previous class, maybe not your solid mechanics class, but maybe your physics class. Okay. So let's look at a spring. Okay. In particular, let's look at the equation that governs a spring's behavior, which is called Hooke's law. So visually, you have a spring. And so one end of the spring will be fixed to the wall. Okay, so that's the left side. On the other side of the spring, we're going to pull it. And so we're going to apply a force F. Okay. In this case, F is a tensile force. And so we're going to be extending the spring, right? Hooke's law is equally valid in compression as well. So if you were to push the spring into the wall, it would follow the same law, just that the deformation would be on the other side. Okay. And so as a result of pulling the spring, what the spring is going to do is that it's going to extend, right? It's going to get longer in length. And so this endpoint right here in green, when the spring is resting, that endpoint might be at that location, but when you pull it, the endpoint may travel a certain distance like that. Okay. So this distance right here is D. Okay. Where this D right here is the amount that the spring elongates in response to the force. All right. And so Hooke's law basically is the relationship between the amount of elongation and the force that you apply. And so Hooke's law is stated like this. So we have F is equal to K times the displacement. Where this F here is an external force that's being applied to the spring. Okay. This D is well, I defined D right there, but another way we can define D is that this is the amount of deformation that results. Okay, so this is the resulting deformation. Okay. One way to think about the deformation is that the deformation is the response of the spring, right? And so just like most objects, if you apply any kind of external effect to the spring, or any external effect to the object, it's going to respond, right? That's true for kind of most things in general. So if you take a chair and you sit in the chair is going to compress a little bit because it's responding to the weight of your body. Okay. If you go up to some guy in the street and you punch him in the face, he's probably going to respond by punching you in the face. And so, most things have a response to external effects. Right? Some things you can put an equation to. Other things like punching someone else, there's probably no equation for that, but you probably shouldn't be doing that anyway. Okay. And so, of course, there's one more variable in this equation here that I haven't quite defined. And so that's K. And so this K is something that we call the spring constant for the spring. Okay. All right. So the spring constant, I want to focus on the spring constant here. Okay. So the spring constant is an expression of how strong the spring is. Okay. Okay. And what I mean by that is if your spring is, let's say it's made of a very strong material. So let's say you have I don't know, a steel spring, just as an example, right? If you compare that to a spring that's made of plastic, and so you compare that to a slinky. So a slinky is a plastic spring. The steel one is going to be a much stronger, right? And so you expect the steel spring to have a much higher spring constant. Okay. Okay. So why is this important? And so the spring constant here, it's going to tell you basically how much the spring is going to deform for a given force. Okay. And so if you have a very strong spring, so let's say you have a spring made of steel, right? You could apply a lot of force to it, But because the spring constant is so high, its deformation is going to be very low, right? Whereas for a slinky, a plastic spring, if you pull on it with just a modest amount of force, it's going to displace a lot because a plastic spring has a very low spring constant. Okay. Okay. So I want to kind of generalize this idea, right? And so Hooke's law, quite simple, right? So we have three variables, and they all kind of have a role that's very clear to see. Okay. Another way to look at the spring constant is that it's you can almost think of it like a proportionality constant that relates an external effect to the object's response. Okay. You can almost think of it as the mathematical link between the two, right? So you apply an external effect, your object is going to respond, and how it responds depends on whatever this proportionality constant is. Okay. Okay. So that idea I want you to kind of keep in your head. It's kind of central to understanding what the stiffness matrix is going to be. Okay. All right. So let's generalize this. And so, for this example here, we had just one force being applied on one side. The spring was fixed on the other side. Let's generalize this to, let's say that neither side of the spring is fixed. And so one way that we can say that is we're going to generalize to 2 degrees of freedom. Sorry about that. I think it was lagging a little bit. Okay. All right, so I'm going to draw the spring again. And instead of only measuring deformation on one side, let's measure deformation on both. And at the same time, let's say that we apply a force on both sides. We're going to apply a force and use different colors here to kind of highlight it. So let's say we apply a force F1 on the left side, and we apply a force F2 on the other side. Okay. And then in response, let's say that the right side or the left side is going to deform by an amount d1. And the right side is going to deform by an amount d2, right? So F1, F2, d1, and d2. Okay. Okay. So let's take the system and let's take what we know about Hooke's law and let's try to form a relationship between F1, F2, and d1 and d2. Okay. So that's the main question that we're looking to answer right now. Okay. Okay. So to do this, let's look at a specific case just to make the equations a little bit easier to form, right? So let's look at a case where our spring is in static equilibrium. So our spring is not moving. Okay. And the conditions for being on static equilibrium is that all of the external forces applied on the spring are going to cancel out. Okay. All right. And so that changes our expressions for F1 and F2, right? All right, and so if we're going to have them cancel out, we're going to have them be equal in magnitude and opposite in direction, okay? So that means F1, we'll say F1 is being pulled to the left. The exact direction doesn't really matter. Okay, so we're going to say F1 is going to be a magnitude of T being pulled to the left. And on the right-hand side, we're going to have a magnitude of T, but going to the right, okay? T stands for tension. Okay. But we're still going to measure the deformation, D1 and D2, okay? So I know I drew D1 and D2 both going to the right. That's just merely to indicate the positive directions for D1 and D2, okay? In reality, you know, if you pull the spring in tension, you know, this left node right here is gonna deform this way, right? All that really means is that D1 is just going to be negative. But the convention I'm doing here is that I'm just drawing the positive directions for D1 and D2. Okay. Okay. All right, so now we have the situation, right? So the forces are equal and opposite on both sides. So let's use this information. So let's relate T to the displacements. Okay. And the equation that we're going to use is Hooke's law, right? Hooke's law just relates the force to the deformation. Okay, so according to Hooke's law, the tensile force T that we're applying on this spring on both ends, this is going to be equal to the spring constant multiplied by delta. Okay. Right, so everything here is defined. So we know T, so T is just the force that we're applying to the spring. You know, even though we're applying on both ends, what we're saying is that we're applying one tensile force. So that's just T. K is the spring constant, and this delta here represents the total deformation of the spring. Okay. All right. So when we were looking at the first spring today, you know, that spring that was fixed to the wall, you know, the deformation was just how much that right side was deformed, right? Let me scroll back up here just to kind of show you what I mean by that. And so in our original example here, if zoom, come on, I scrolled up like 10 seconds ago. Anyone does this. Okay, we'll use your brain, right? So if you scroll back up in your notes, the very first spring that I drew for you, you know, the left side of that spring was fixed to the wall, right? And so by being fixed to the wall, that means that side's not going to move. And so whatever deformation that the spring is going to undergo, it's going to be all captured in that right node. Okay. Thank you. What? Now it's just messing with me. Oh, there we go. Okay. All right, so you can see from this image here that, you know, because that left side is fixed, you know, however much the spring is deforming is captured by that right side. Okay. We don't have that case with our spring now, right? And so with our spring now, that left side is no longer fixed to the wall. And so both ends of the spring are able to deform. Okay. All right, it's back. Good. Okay. And so when we come back to this equation right here, you know, this total deformation, we need to be a little bit careful in how we define it. Okay. All right. And so, you know, we have 2 degrees of freedom here. We have D1 and D2, right? The total deformation of the spring is going to be the difference between D1 and D2. Okay. And so this delta here is going to be D2 minus D1. I made D1 negative because, you know, we know that D1 is gonna, we know that the left side is gonna displace to the left because that tensile force is pulling it to the left. Okay. All right. And so if we plug that in, then we get T is equal to K times D2 minus D1. Okay. All right. So that's good. So that's a good place to be. Now let's use this equation here and relate F1 and F2 to T. Okay. So there's a lot of diagrams of springs kind of rolling around. So let me kind of let me draw it again here. Okay. And so originally when we first drew our 2 degree of freedom spring, you know, it looked something like this, right? So we had our spring. Okay. We had our deformations like this. Okay. D1, D2. And the way that we defined F1 and F2 was like this, right? So F1 was the force that we're applying on the left side of the spring, and F2 is the force that we're applying on the right side of the spring. Okay. Let's relate this to the directions for T. So actually, let me overlay T here. Okay. So the way we've set up our equilibrium problem, that T is pulling the right side of the spring over to the right with a magnitude T. Okay. Meanwhile, we're also applying a force in the negative direction of T on the left-hand side. Okay. All right. So what does this tell us? And so this tells us that just based on the directions is that F1 is equal to minus T, right? Because F1 and T are in opposite directions, and so we need that minus sign there. Meanwhile, F2 is in the same direction as T, and so we can say that they are equal. So F2, what we defined as the force applied on the right-hand node, when we apply it to our case of static equilibrium, is in the same direction. Okay. Okay. All right. So now what we're going to do is we're going to plug in for T. Okay. And what we're going to plug in for T, we're going to plug in this expression that we had up here. Okay. So we're going to plug in for here and plug in for this right here. All right, because remember, you know, our goal in doing this derivation is to get a relationship between D1, D2, and F1 and F2. Okay. T was kind of just the stepping stone in order to get. Okay? So because as soon as we plug in for T, we're going to eliminate T from these equations, and then you know, get an expression with just F's, D's, and K. Okay, so when we plug in for F1, we get F1 is equal to minus K D2 minus D1. And then we got F2 is equal to positive K D2 minus D1. Okay. All right. For our F1 equation, I'm just going to distribute that negative. And so just so that we have a positive number out in front. So you have F1 is equal to K. If we distribute that negative inside the parentheses, D1 and D2, we're going to swap places. And so we have a positive D1 minus D2. Okay. All right. So now what we have here are these two equations. So we have F1 is equal to K times D1 minus D2, and F2 is equal to K times D2 minus D1. Okay. We now have two equations that we can put in matrix form. Okay. And so in matrix form, this looks like this. We have F1 is equal to K times D1 minus D2. That's our first equation. Our second equation is F2 is equal to K D2 minus D1. Okay. I'm stacking the equations one on top of each other just to make it a little bit easier to see when we put in matrix form. Okay. All right, so in matrix form, this looks like the following. So we have F1, F2 is equal to positive K, minus K, minus K, positive K. Okay. That's our matrix. And our vectors is D1 and D2. All right, so if you perform the matrix vector multiplication on the right there, you'll see that we're going to obtain those exact equations. So let's put a box around this. This is kind of the end of the derivation there. Yeah.
You get K minus K and then minus K at the bottom.
Yeah, good question. So those K's there are the coefficients. And so actually it might be a little bit easier if I rearrange the second equation right here. So I might kind of line up everything in the same column. So D2 minus D1, another way to say it is minus D1 plus D2. And if we distribute the K through these ones, we get F1 is equal to K D1 minus K D2. And then F2 is equal to minus K D1 plus K D2. So you can see the top equation, you have K1, yeah, positive K, minus K, positive K. Yeah. Okay. And so what I want to draw your attention to is this entry right here. Well, actually, first, before we do that, let's kind of write this in shorthand notation. So we have an F vector or force vector is equal to a K matrix. And so the way I indicate matrices, I know I'm in the minority with this, but for me it makes the most sense. I put an underline. So if I put a symbol with an underline, that means it's a matrix multiplied by a D vector. Okay. So this what I've drawn right here, and there's kind of a lot going on. So let me circle it in orange. Okay. What I've boxed in orange right there, that's kind of the generalization of what we just drew. Okay. Let's look at this equation, because where we started this whole day was we were looking at Hooke's law, right? So remember, Hooke's law is F is equal to K times D. Okay. Where F was a force, K was a spring constant, and D was the displacement. Okay. This looks pretty similar, right? And so this basically is the exact same equation, except instead of numbers, instead of scalars, we have vectors and matrices to make it all kind of work out in a linear algebra sense. Okay. All right. And so this matrix here, okay, this matrix here is what's called the stiffness matrix. And it's a concept that's used all throughout finite elements. And so if we were to draw it out, the stiffness matrix, at least for a spring, looks like K minus K minus K, K. Okay. Right. And it plays basically the exact same role as a spring constant in 1D. Okay. So remember we talked about, the spring constant is a constant that relates basically how an object is going to respond to an external effect, right? This stiffness matrix plays the exact same role. So when you have a multi-dimensional system, you have multiple degrees of freedom, the stiffness matrix is going to tell you how each of those degrees of freedom is going to respond to an external effect. Okay. Oops. Right. So we'll be working with stiffness matrices a lot, and what you'll see is that most finite element problems will, or all finite element problems will boil down to this kind of simple linear system. So the question then becomes, what is the stiffness matrix, or how do we get the stiffness matrix? All right. Any questions on this so far? Okay. So before I go into a bit of how the stiffness matrix is actually used, let's talk a bit about kind of what kinds of things make up the stiffness matrix. And so we've derived kind of one stiffness matrix here. So this right here is the stiffness matrix for a spring. A spring that has 2 degrees of freedom. But not everything in this world is made up of springs, right? And so that kind of begs the question of, if you have a regular, another object, so let's say this protractor, what's the stiffness matrix of that protractor going to be? Okay, it's gonna look a lot different than this. And so, I can't give you that answer kind of off the top of my head. That would take a lot of computations, but it's useful to kind of know generally what kinds of properties or what kinds of things enter into the stiffness matrix. Okay. All right. So generally speaking, what the things that enter into a stiffness matrix are things like the material properties and the geometric properties of the object under consideration. So for our spring, a spring really only has one relevant parameter, and that's its spring constant, right? And a spring constant is a material property that tells you how much the spring is going to deform in response to external forces. Right? And so it makes sense that our stiffness matrix has that spring constant inside of its structure. Okay. But if you talk about kind of another object, so one thing that we're going to start next week is going to be trusses. Okay. So just jumping ahead a little bit, but just kind of illustrating this to you. If you don't know what a truss element looks like, it's basically just a very slender structural object. Okay. Right. So it's a rod is a very good example of a truss element. Okay. For each truss bar, we're usually interested in its length. We're usually interested in its cross-sectional area. Okay. And we're usually interested in the type of material it's made out of. Okay. And we can summarize that with its Young's modulus, or its modulus of elasticity. Okay. All right, so all of the properties that I've listed, the length and the area are geometric properties. The Young's modulus, or the modulus of elasticity, that is its material property. Okay. The stiffness matrix for a truss is a combination of these properties here. And so the stiffness matrix is E times A divided by L multiplied by the matrix 1 minus 1 minus 1. Okay. So that EA over L is multiplying the entire matrix. And so you can see here this EA over L is all the material and geometric properties. Okay. So that's true for most what I call kind of physical FEA. So that's kind of what we're doing, is we're taking kind of physical systems and we're performing FEA, right? And this is true even for, even though, for this class, we're going to focus mostly on structural mechanics in the first half. Second half, we're going to do heat transfer, but it's also true for fluid mechanics as well. And so no matter what kind of FEA that you're doing, whether it be thermal, fluids, structural, electromagnetism, your stiffness matrix, the exact form is going to be different in all those cases, but it still follows the same trend, is that, whatever material properties, whatever geometric properties you have, it's going to be factored into the stiffness matrix in some way. Okay. Because, if you think about it, the stiffness matrix tells you how the system is going to respond, right? And how an object responds to external stress depends on its geometry, how big it is, how small it is, its shape. And it's going to depend on its material, whether it's a strong material or a weak material, right? So it makes sense that all of these things are part of the stiffness matrix. Okay. So that's an important point I wanted to cover, that the stiffness matrix, we'll be going over different stiffness matrices for different types of elements, but just know that this concept kind of generalizes and extends to all different kinds of analysis. And it kind of has the same property where, you have material and geometric properties inside the stiffness matrix. All right, any questions on this so far? Okay. All right, so let's move on to the next point, which is multi-element systems. Okay. So the stiffness matrix that I just showed you, right? This is valid for one what we call element. Our element in this case being a spring, right? So if you have one spring, you just need one stiffness matrix to describe, how that spring is going to behave. Okay. But what if you have a system where you have multiple springs connected to each other in series? How do you analyze such a system? And so let's say that we had something like this, and we'll say this is an example. Okay, so I'm going to use this example to kind of illustrate how to handle multi-element systems. Okay, so let's say that we have a situation where we have a fixed wall. Okay, so that's usually my indication for a fixed wall. It's a line with kind of slanted lines. It tells you that that wall is not moving. Okay, we'll say we have one spring attached to this wall. We'll call this element A, and we'll say element A has a spring constant of Ka. But then connected to the spring, let's say we have another spring. We'll call this Kb. Okay. And then on the end of this spring, we're going to be pulling on it with a force. We'll call it F. Okay. Okay. And then if we label the nodes, let's say that we label the leftmost node, node 1, the middle node, node 2, that's the node in between the two springs, and then the rightmost node, node 3. Okay. We can quantify their distances or their deformations. So we'll say that the deformation of node 1 will be d1, the deformation of node 2 will be d2, and the deformation for node 3 will be d3. Okay. All right. So we have two springs here. We're applying a force, and what we're interested in is we're interested in determining how each node in the system is going to deform. Okay. We're going to compute. D1, D2, D. Okay. All right. So we're going to use the concept of the stiffness matrix, but since we have two elements here, we have two springs. That means we're going to have two stiffness matrices as well. Okay. So what this problem is about is, how are we going to combine the stiffness matrices from two separate elements connected by one node. Okay. Any questions on this example so far? Okay. All right. So let's go and get started. So let's start. So we have two springs. So let's write out the stiffness matrix for both springs. All right, so I've labeled the springs A and B, so let's do the stiffness matrix for spring A. Okay. So for spring A, what we have is F1, F2 is equal to. Spring constant for spring A is Ka. We have Ka minus Ka minus Ka and Ka. And we're going to multiply by the displacement response. So this is d1 and d2. Okay. All right, and then for element B, we have to be a little bit careful here because element A you can see is connected to nodes 1 and 2, right? So if I were to box this. So element A is connected to nodes 1 and 2. That's why we use D1, D2, and F1 and F2 in our matrix. Okay. Element B, on the other hand, is connected to nodes 2 and 3, right? And so that's going to change how we do our matrix a little bit. And so for element B, we're going to have F2 and then F3, okay? Because F2 is on the because node 2 is on the left of node B of element B. And node 3 is on the right of element B. Okay. This is equal to its stiffness matrix, so positive Kb minus Kb minus Kb, and then positive Kb. Okay. And it's going to be equal to, this is going to be multiplied 2 by the vector d2 and d3. Okay. Okay. So each of those matrices individually govern the behavior of each of those elements, okay? But we're not analyzing them in an isolated system, right? Both of these springs are acting together in one structure. And so we want to get their kind of combined effect, right? And so ideally what we would want is we would want one stiffness matrix for this entire structure. Because if we can get one stiffness matrix for the entire structure, we'll be able to analyze it all together and get the entire system response. Okay? All right, so something like that would look like this. And so, we have three nodes. We have three nodes in the system. We have node 1, 2, and 3. And so our one stiffness matrix is going to be a 3x3 system. We're going to have F1, F2, F3. Is equal to. We don't know what's going to go in here just yet. We're going to fill that in a second. But we want to get a relationship between the nodal forces, F1 through F3, and the nodal displacements, D1 through D3. Okay. The big question mark is going to be what goes in the middle of these. And so this right here is going to be some 3x3 matrix. It has to be 3x3. It has to be 3x3 in order for the dimensions to work out, because this left-hand side matrix is 3x1, and this other matrix here is 3x1. Okay. And so in order for the dimensions to make sense, our middle matrix there must be a 3x3 square matrix. Okay. All right, the question is, how do we obtain that square matrix? Okay. So the good news for us is that, in determining this bigger 3x3 system, the way we're going to do that is we're going to kind of combine together the stiffness matrices from our smaller systems. Okay? Individual element stiffness matrices. So we're going to take each of the individual stiffness matrices and fit them in. Okay. The key, or the thing that's going to tell us, where to put these, because if we look at the individual element stiffness matrices, those are each 2x2 matrices, whereas our global stiffness matrix is 3x3. So there's their sizes don't match up. Okay. The locations of these matrices will depend on which nodes that each element is operating. Okay. All right, so let's go one by one. So we'll go element A, then element B, and we'll see how to kind of slot those in. Okay. Let me redraw the system here. And I'll draw it a little bit bigger This makes it a little bit easier to draw. And so our global stiffness system, or our single stiffness system for our entire structure, is 3x3. So we have F1, F2, F3. We have kind of this mystery matrix in the middle. And then we have the corresponding displacements, D1, D2, D3. Okay. So let's start with element A. We know from the diagram at the beginning, element A acts on nodes 1 and 2. Meanwhile, element B acts on nodes 2 and 3. And so those are going to tell us kind of which rows and which columns we're going to insert those element stiffness matrices. And let me actually label the columns to actually make it more a little bit easier to see. And so we can see the 3 rows. And so we can see the first row is our D1 row, our second row is our D2 row, our third row is D3. Okay. We have the same convention for the columns. So we have a D1 column, a D2 column, and a D3 column. Okay. The first column being D1, the second column being D2, the third one being D3. All right. Let me write out the element stiffness matrices for elements A and B one more time. So element A, we have F1, F2, equal 2, Ka minus Ka minus Ka, Ka, D1, D2. Okay. Okay. So since element A acts on nodes 1 and 2, this tells us that, you know, this 2x2 matrix, this Ka minus Ka minus Ka, Ka matrix, this where we're going to insert this is on the D1, D2 row and the D1, D2 column. Okay. So let's go back up to our system here. Okay. And so the D1, D2 rows, that's rows 1 and 2, and the D1, D2 columns is columns 1 and 2 as well. Okay. So let's draw a box around it just to make it a little bit easier to see. Okay. And so if we were to block out the sections that is the D1, D2 row and the D1, D2 column, it would look just like that. Okay. And then from here, we can write out the entries of our element stiffness matrix. And so we're just going to write the entries, just copy it right over. So we have Ka minus Ka minus Ka and Ka. Okay. Meanwhile, if we look at element B, so element B is connected to nodes 2 and 3. So we have F2, F3, okay, is equal to Kb minus Kb minus Kb, Kb. Okay. And then we have D2, D3. Okay. Use a different color for this. Let me use blue. Okay. All right. And so just like we did with element A, we're going to insert this into the appropriate rows and columns. And so element B we know is D2, D3. So let's go ahead and highlight those. So that's the second and third row and the second and third column. So if we were to box that out, it would look like the following. Okay. And just like we did with element A, and everything that we've boxed there, we're going to insert the entries of our element stiffness matrix. Okay. But we have one complication here. So we have an overlap. So we can see that the upper left square of this matrix is overlapping with the bottom right square for element A. Okay. That's perfectly fine. So you can have overlap. And so whenever you have overlap, all you need to do simply is just to add the two entries together. And so that middle entry in the second row and the second column, instead of just being KA, is going to be KA plus KB. KA. The KA is contributed from element A. And we have KB being contributed from element B. Right, and the rest of the entries of the matrix stay the same. So you have minus KB, and then a positive KB. Okay. All right. Everything that's not boxed will just become 0. And so we have a 0 in the top right and a 0 in the top and the bottom left. Okay. All right, and so that is how assembly works. And so we've taken a multi-element system and we've combined their contributions into one stiffness matrix. Okay. All right, any questions on this? Okay. All right. So we're in good shape. And so we're at here now, right? And so by assembling all the element stiffness matrices, we have one system here. Okay. Ultimately, what we want is we want everything that's to the right here. Okay. And so we want to solve for D1, D2, and D3. Right. That's still our goal. And typically speaking, we know everything on the left. And so all the external forces, we know this. So everything here. We know this. So that's either given to you in the problem, or it's given to you just in whatever physical situation you're analyzing. Okay. Because remember what that vector represents there is that F1, F2, F3. This represents any external forces or external effects that you're applying on the system. And normally you know this just because that's just the nature of the analysis that you're doing. Okay. And so in order to solve for D1, D2, D3, what we need to do here is we need to solve this linear system of equations. Okay. Because even though we have it in matrix form, just kind of for convenience of writing, right? This matrix here represents a system of 3 equations and 3 unknowns, right? It represents an algebraic system. And so in theory, if you have 3 equations and 3 unknowns, you should be able to solve for the 3 unknowns, right? And so you can write this out in equation form. You can do direct substitution, and you can solve for those unknowns. Okay. A better way that we're going to use in this class is we're going to use just the matrix properties. Okay. And so one way to solve this is if we have some F vector is equal to some K matrix times D vector. Okay. And we want to solve for D vector, right? One way to solve this linear system is to just simply invert the matrix. And so this is going to be equal to our K matrix inverse multiplied by F vector. Okay. So that's typically what we're going to do. And so, and the reason for this is that this operation right here, computers can do this really well. In particular, MATLAB does a really good job of this. They can even invert matrices, which is normally a pain in the ass, but for a computer, it's actually pretty easy to do. I shouldn't say easy. It still takes a lot of computation, but you know, from the user side, from the engineer side, you know, it's just one line of code. So that's pretty simple. Okay. All right, and so it seems like we're done then, right? Because we know what all of these are. So we know F, right? That's usually given to us in the problem. We spent all this time, you know, we just kind of went through that whole exercise of assembling the linear system, so we know what K is. And if we know what K is, if we throw it into a computer, we can take its inverse. Okay. So everything on this side of the equation is known. Okay. We have everything, right? And so we should be done, right? Well, you know, I'm of course I'm kind of hinting at it because we're not done quite yet. Okay. If you look at our system up here, right? If you look at this matrix, right? What you should notice from this 3 by 3 matrix, and let me kind of put a highlight around it so you can see. Okay. So what you should notice from this matrix right here is that it is symmetrical. And what a symmetrical matrix means is that if you were to draw a dotted line that goes right down the diagonal of the matrix, okay, you kind of split the matrix as if it were like a ham sandwich or something, right? What you should see is that all the entries on the top half of the matrix, right? The top triangle, the top right triangle is a mirror image of everything that's on the bottom left, right? So this KA is the same as this KA, this KB is the same as this KB, okay? 0 is the same as this 0, okay? So you have a symmetrical matrix. So symmetrical matrices are they're a lot of things. But one thing for sure that a symmetrical matrix is that it's non-invertible. So if you try to take the inverse of a symmetric matrix, okay? In other words, you know, you try to take this, this right here, okay? This particular operation, K inverse. This is going to be impossible. And even if you were to throw this into MATLAB and try to take the inverse of a symmetric matrix, MATLAB will give you an error message. It says, you know, you can't take the inverse of a symmetric matrix, idiot. It'll leave the last part out, but that's kind of what's implied. And so we're not able to invert this matrix. Okay. In terms of linear algebra, what this basically means is that our equations are not sufficient enough to solve the system. Right? So even though we have 3 equations, you know, there's some redundancy in our equations that makes it unable to solve. Okay? Metric tells us. Because, from an algebraic standpoint, if you have, the same number of equations at the same number of unknowns, and in this case, we have three unknowns, we have D1, D2, D3, and if we have three equations, we should be able to solve it. That's not necessarily true in all instances. And so if you have kind of multiple equations are kind of redundant to each other, that's not possible. Okay. So how can we do this? And so how do we get around this situation? What this kind of implies to us is that we need to modify our equations a little bit in order to make it solvable. And so how are we going to do that? Is there any information in the problem that we haven't taken advantage of yet? There is. In fact, I've kind of glossed over it a couple times, but the information that we haven't taken advantage of yet are all of the external effects, right? So if you scroll all the way back up to our original problem here, right? There's two pieces of information here that we haven't used quite yet in our linear system. I wish I didn't use so many colors here. Let me kind of erase some of the colors just to make it a bit more clear. Okay. All right, one piece of information we haven't used is the fact that the left side of our structure is fixed to the wall. Right? So node 1 is actually fixed. Okay. That's an external effect. And so an external effect is any kind of effect that's affecting our structure from the outside. Okay. The other piece of information that we haven't used yet as well is the fact that we're pulling on the spring to the right. So this right here is an applied, I call it an applied load. Okay. So we haven't incorporated those pieces of information into our analysis yet. The only thing that we've done is we've incorporated the two stiffness matrices for the springs, and we've seen how they interact mathematically through the assembly of the matrix. Okay. But in order to kind of complete the problem, in order to make it solvable, we have to include these external effects. Okay. And kind of the general term for these kind of external effects are boundary conditions. So that's the next step. Okay. So we have only about 4 minutes left, and so I'll introduce the idea of boundary conditions, but we'll see how they work out mathematically on Tuesday. Okay. So boundary conditions is another name for any kind of external effects that are having an impact on your system's response. Okay. Because in reality, you can have lots of external effects, but not all of them are going to have a response, or not all of them are going to cause a response for the types of physics that you're going to be looking. Okay. And so, for example, if you have a structure and you heat it up, so let's say that you throw in a microwave for some reason, right? It's going to change its thermal properties, but it's not going to have as much of an impact on its structure. Okay. So it's important to distinguish between which external effects are going to affect the system that or the physics that you're looking at versus the ones that aren't. Okay. And there are two types of boundary conditions that we're going to be looking at. So I will say, I'll preface this by saying I didn't choose these names, so they're named after people. And scientists love doing that throughout history, naming things after themselves, but I think it just makes them hard to remember. But because it's these terms are going to come up a lot more. Usually I don't like using these terms, but because this is 541 and these terms are going to come up a lot more, we'll use their proper names. And so the first type of boundary condition is called a Dirichlet boundary condition. So a Dirichlet boundary condition is one that directly specifies the solution variable or solution value. Okay. We'll talk more about what that means on Tuesday. And the other boundary condition type is called a Neumann boundary condition. So it's Neumann. Okay. So these are external forcing effects. I'll put forcing in quotes. That influence. So these two definitions sound similar, but directly specifying the value is different than having an influence on the value. Okay. So one is a little bit more direct, the other one kind of relies on physics to kind of determine the effect. Okay. All right, and so I'll tell you that in our example right now, we have one Dirichlet boundary condition and one Neumann boundary condition. Okay. And so on Tuesday, we'll see what those ones are and how they affect our system. Any final questions before we wrap it up for the week? Okay, all right, so that's all we have time for today. So thank you guys for coming out. On Tuesday, we'll pick this up and we'll finish up this example, and then we'll move on to truss equations. Thank you guys for coming today. I hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend, and I will see you guys on Tuesday.
Good. You want this?
Thanks, Brianna.
Actually, you still have it. No, I'm gonna throw it away. You want it? So yeah, I was like, not really.
Thanks, Jim.
Maybe you could ask someone else. No, I'll take Oh, you had it. Yeah. The same line.
Bye. Good weekend.
Which is.
You too. See you, Trevor. See you guys. Have a good weekend.